Today I'm going to be doing a demonstration of our laboratory scanning kit. So on my computer screen you can see that I have opened up HyperSpec 3, and I'm going to start using HyperSpec 3 with a SWIR 384 that has a 25mm lens on it. And I'm going to start by looking at a live video of the focal plane array. And this live video screen shows a two-dimensional image of the focal plane array, where this dimension is the spatial dimension, or all of the spatial pixels on the focal plane array, and this dimension is the spectral dimension. And if you click the crosshair, you can see a cross-section of the spatial dimension over here, or the spectral dimension over here, or the spatial dimension down below. And this will show you the light intensity on every pixel in the two-dimensional focal plane array. And on this screen you can also set the exposure time and the frame period for the camera. I'm going to start off by adjusting the focus of the camera to make sure that I'm focusing on the same plane as my sample. And usually to do this focusing, I use a handy-dandy target that is a bunch of periodic black lines that allows us to easily focus a line scanning camera, which is harder to focus than your average 2D array camera. So if I place and then adjust until I get the sharpness of the lines here to be as deep as possible. So you can look at two different locations. You can either look at the image of the focal plane array to see the lines getting sharper rather than blurry, or you can look in the spatial dimension and get the depth of these peaks to be as deep as possible. And oftentimes I will also zoom in and when we have things in good focus, I can move on to setting the exposure time. Generally, when I set the exposure time, I like to look in the calibration window, which will give me a histogram of all of the intensity values of every pixel on the focal plane array, which will give me absolute confirmation that I am not saturating anywhere on my focal plane. Where sometimes you can trick yourself if you are looking at not the most intense cross-section on the live video chart up here. So I can move the exposure time up and down. If the exposure time is too high, I can see here that I am saturating my my pixel at many points. You can see that both on the 2D projection and on the histogram. And you can see the characteristic flat line of a saturated spectrum. If I am underexposed, you can see that the focal plane is quite dark. You are not using much of the dynamic range of the sensor, and my entire focal plane array is on the low end of the histogram. In general, we like to set it so the maximum intensity when looking at a white spectral on target is approximately 80 to 85% of saturation to ensure that you remain in the linear regime of the sensor. And this exposure time achieves that. At this point, now that I have set the focus and properly set the exposure time, I will collect my white and dark references. So the dark reference is gathered by placing a lens cap over the lens to collect an image of the focal plane when no light is getting in, and this is used to correct for the dark current of the sensor. Next, When looking at a white target, and we usually provide a spectral on target with our scanning kits, take an image where the full frame is being occupied or is being filled up by a uniform white target. And when that is being done, you click white reference and collect a white reference that can be used to convert the data from raw digital counts to reflectance. And I'm not going to do that right now because I've already done it. Once the scan parameters have been set, you can go ahead and close the calibration window and open the capture window. And in this window, we can set all of the capture parameters for our data acquisition. So there are a number of lines here. The prefix barcode is a prefix that will be appended to every data folder when data cubes are saved. So when data cubes are saved, by default, they will go to C, Headwall, Sensor 1, and it can be up to Sensor N if you have multiple Headwall sensors on your system, and then Sensor 1, and then all of your white and dark references will be stored in the calibration folder, so if you want to go back to previous white and dark references, you can do that. And the most recent white and dark reference will always be used when saving your data. In the capture folder, you will save all of the captured data, and inside that folder, you will save the raw digital counts in a file called raw. The reflectance data, if you select to do the reflectance conversion while you are doing the data collection, will be called data, and the white and dark references will also be put into the same folder, along with settings header file that will supply information on the capture parameters that were used during data acquisition, and an RGB or a quasi-RGB image of the scene. And so now one important thing, because this is a line scanning system, is that we want to properly set our scan speed such that every time the stage moves one spatial pixel, we collect a new frame, so we acquire square pixels in the image. And we can do that automatically by, again, placing our handy focusing target in the view of the sensor. And this focusing target has lines spaced by exactly 1 centimeter. And our software will, knowing that the lines are spaced by 1 centimeter, be able to calculate the spatial pixel size on the sensor, and therefore be able to calculate the field of view and the sampling distance, or IFOV, which can be used along with the frame period to calculate the speed. And the speed is, of course, the IFOV divided by the frame period. And if you hit this calculate button, if your 1 centimeter spaced lines are in view of the sensor, you will automatically calculate the correct device speed. And I'm actually going to mess up the device speed right now so you can see that it's actually calculating something. So now when you hit the calculate button, it will calculate the proper device speed for the sensor. At this point, it is often desirable to view the waterfall window. Now, the waterfall always shows the current view of the sensor, which is 1 line, along with a history of many of the last lines that the sensor has seen. So if the stage is moving and you're sweeping past a sample, you can see a live view of what the sensor has just seen, and be able to actually see what an image will look like when you're done capturing. So you can look at the waterfall window while also using the motion tab to move the stage. And if we set the speed in the motion tab equal to the speed for square pixels, we should see square pixels. And now if I select a position, either by typing it into the position box or by moving the slider bar, the stage will move to my desired position. And as the stage sweeps past the sample, you can see an image of the samples showing up in the waterfall view. And we can see that our sample is nicely centered in the field of view of the sensor. So it looks like we are ready to collect some data. And so we'll just go back to the 0 position, again moving the slider bar back to 0, and observing our samples showing up on the waterfall view. And now I'm going to name my sample. So this sample set is a series of white powders that we are going to differentiate by using our shortwave infrared sensor. So I'm going to call this sample set white powders. So I often set the start and stop position while looking at the waterfall and using the motion tab. So if I want to find the last position in if I want to find the last position or the end of my scan, I will usually enter in a large number and watch as the sensor moves past my sample. And when I have collected enough of the sample, I will hit halt. And here I see that I've collected my entire image by the time I reach the position of 225 millimeters. So that will be my end position. And now I can go back to the home or 0 position. And when I get to the beginning of my image, I will hit halt again and enter that number as my beginning position. And here at a position of 40, I have seen all of my image. So now that I have set my scan parameters, and so now that I have set my focus, my exposure, and my scan parameters, I'm ready to capture a data cube. Simply by pressing go, the stage will move past the sample, and when you have scanned the entire range, the data cube will be saved in the C Headwall Sensor 1 folder, and an RGB image of the cube that was just collected will pop up when the scan has completed. And so now we can go back into C Headwall, C Headwall, back to Sensor 1, then captured, and we can see our white powders folder appears here, and we have our data folder, the raw digital counts, the white and dark reference, and our settings file, and that same image to see what we have just collected, all saved in the data folder. Well, if the scan speed is too fast or too slow, you will not get square pixels. If it's too fast, your spatial pixels will be scrunched in the travel direction, and if it's too slow, they will be elongated in the travel direction. So first, let's set a scan speed that is much too fast and see what that looks like on our waterfall view when we pass over our image. Here you can see that the white powders are scrunched in this image or when the stage is scanned too fast. And let's see if I can scan even faster. So you can really see the image is scrunched now, and you actually get less resolution in the travel direction then because you're scanning too fast. And now if you scan too slow, you will be elongated in the travel direction. So this, of course, takes longer to demonstrate because we are moving the scanner slower. Well, you can see instead of having nice round cups, we have elongated oval-shaped cups. Because again, we are scanning too slow, which elongates the pixels in the direction of travel. So now I'm going to open up our newly acquired data in Spectral View, Headwall's data processing program. So that the simplest way to do that is just to double-click on the data file. When Spectral View opens, you get a pop-up window that allows you to select what data to load. Usually you just want to press Select, which will load all of the wavebands in the entire data cube, so you can work with all of the information that you've just gathered. If you've collected an exceptionally large data cube, you can load smaller regions. So say you only want to load from 1500 to 2500, you can do that as well. And now you've just selected a portion of the data cube. But for now, we are going to load the entire data cube. If you have loaded a raw data cube, you can apply the white and dark references at this point to generate a reflectance data cube, but since I'm already loading the reflectance data cube, these are grayed out. And you can also do spatial binning to only load a portion of the spatial data cube. Here you can see the image that we have just collected and an RGB representation of that. The red, green, and blue pixel values can be chosen down here, or you can view the image in a grayscale, where this is a grayscale image of each of the spectral bands. The other thing that can be done in Spectral View is you can view the spectral response at any of the spatial pixels by opening the spectrum window and mousing over any of the spatial pixels. And if you click on any of the spatial pixels, you can save the spatial pixel from that location in the spectral window. And so now we can see here a single spatial pixel from each of the different white powders. And we can even use this these spectra to select some other RGB bands that might give us more contrast for our family of white powders. And so I'm going to try selecting, changing to 2050, and 2167, and let's say 1564. And you can see that by selecting these different red, green, and blue pixels, I can get a bit more contrast on the image. Again, just by displaying three bands, one is the red band, one is the green band, and one is the blue band. Another feature of Spectral View is the classification module, and so you can open up the classification module with Tools, Classification. You can select an existing model, which I'm going to do right now, because I've previously created a model for this set of data. Again, select all of the bands, and I'm going to select Flip because I want it to pop up the correct way. And so this is what a good finished model of the spectra can look like. Okay, so now I'm going to start with a fresh the spectral model and show you how to generate this yourself. Choose a folder for it, and why don't we just put it where the data is. So C, Headwall, sensor 1, captured in with the white powders, and there we go. Right. So here we have a blank model with no classes having been made yet. So to create a new class, you hit the green plus button up here, and then give it a name. After you give it a name, you can click on the color and give it a color. And then to give it a spectrum, you have to select a spatial pixel to be your seed pixel, and then the classifier will perform spectral angle mapping, comparing that one seed pixel to all of the pixels in the entire image, and it will find all of the pixels that pass the spectral angle mapping threshold set up here. So if I hit update, I can see that. And now every pixel that has passed my threshold is in green, and I can see that I mostly just have pixels that are in my cup. And if I zoom in here, I can also spatially exclude some pixels that I might not want to include in my model. And if I do that, I can hit recalculate. Now, all of the green pixels have passed my SAM criteria and my spatial criteria, and the red pixels have passed my SAM criteria but are excluded because they are not in my selection box. And when I have acquired the proper amount of pixels, and I can see right now that I am generating a spectrum that is the average of 2,199 spatial pixels, and I can see my seed pixel spectrum in green up here, and my calculated reference spectrum in black, which is the average of my almost 2,200 pixels. After I click update, that average spectrum has been saved, and if I click save, I will save my model. And then when I click classify, I'm going to compare that reference spectrum to all of the spatial pixels in my hypercube, and I'm going to create a false color image that will be that will have the color assigned to each class in every spatial pixel that passes the spectral angle mapping criteria. And so here I can see that I have generated a nice map of where the sodium bicarbonate is in my image. And in the same manner, I can create more spectral classes. So I select a new color. I hit Update Spectra. I think I've selected a good amount of pixels here. I will hit Update and Save and Classify. And now I have also classified the sucrose. Now here's my sodium chloride. Oops. Currently, I am changing the the spectral angle mapping threshold, which will increase or decrease the how similar the spectra need to be in order to be classified with that given class. And I can change the limits up here after I've created my model as well. And now I've created a fairly quick and pretty good model to locate all of the 6 white powders in this example. And now I'm going to collect another image with with some of the powders mixed with others. I'm going to call this white powders mixed. I haven't moved my samples, so all of my positions are good to go, and I'll just press capture. At this point, I'm going to open up my new spectrum using my model. And here I can see where I have mixed the ammonium nitrate in with the sodium bicarbonate, and I've mixed the sodium bicarbonate in with the sucrose here. And you can see that it is all appearing in the classification model.